Okay, hello everyone. So let us now discuss the Wronskian. Now, the Wronskian is another way to determine a linear dependence or independence. Now, it makes use of the concept of matrix determinant. Okay, so in this lesson, we will go through the definition, how to set up the Wronskian, and how to interpret the determinant that we get to determine if a set of functions is linear independent or dependent. Okay, so let's go to the definition first. Okay, so for the Wronskian, suppose that each of the functions f1 of x, f2 of x, through fn of x possess at least n minus 1 derivatives. And the determinant, okay, this is how we notate the Wronskian. And then as you can see here, this is from on the very first row, we have here f1, f2, and fn. Okay, so up until fn. And then you create n by n matrix, okay? An n by n matrix. And then for the second row, we get the first derivative. So first derivative of f1, first derivative of f2, so first derivative of fn, until you get to fn minus 1, f2 n minus 1, and then fn n minus 1. Okay? So that's how you set up the Wronskian. Okay, so these are so we start with f1, and then the second row will be first derivative, and then the second derivative, until you reach f raised to the order of n minus 1. Okay, so and then how are we going to determine if it is linear and independent or not? So after setting up this matrix, we will get the determinant of this matrix, and then let's read the definition. Let f1 of x, f2 of x, and fn of x be n solutions. So these are the solutions to our homogeneous equation. The homogeneous linear nth order differential equation on interval I. Then the set of solutions is linearly independent on I. So linearly independent on I if and only if the Wronskian or the determinant of that particular matrix is not equal to 0 for every x on the interval. Okay, so this can be a little bit tricky. So the only thing that we have to remember here is that if we find um, even a single x value, where the Wronskian is not equal to 0 along the interval, so that means that the set of functions is linearly independent. Okay, so this will be clearer once we do the examples. Now we will do the same examples that we did for the previous lesson, the previous linear independence topic, so that we can confirm our results. Okay, so let's start with the first one. We have right here y1 is equal to x, and and y2 is equal to 5x. Okay, so let's set up the Wronskian. Let's find the Wronskian, I mean. So we have here x and 5x is equal to, so we need to create a 2 by 2 matrix for this. 5x. And then we have the derivative of x, 1, derivative 5x, 5. Okay, so the determinant will be equal to, so this is like that, right? So 5x minus 5x. Okay, so this will be equal to 0. Okay, so no matter what x value we choose, in the interval, so the Wronskian of this particular set of functions, x and 5x, will always be 0. So that means this is linearly dependent. Okay, linearly dependent. So if we can find even a single x value where it is not equal to 0, then we can say that it's linearly independent. But as you can see here, no matter what x we choose, the Wronskian is already 0. Okay, so that would be linearly dependent. Okay, so let's do the second example. So let's see how this differs if it is linearly independent. Okay, because we got the linearly independent result from the previous example. Y1 is equal to x and y2 is equal to x squared. Okay, so let's set up the Wronskian for this one. It's equal to x squared, and we have 1 and then 2x, right? So what is our determinant? We have here 2x squared minus x squared, right? So what do we have? Wronskian of x squared is equal to, we have x squared, right? Okay, so um, if our given interval, it's not given here in the example. In example 3, let's see our interval. So our given interval is negative infinity to positive infinity. So there are lots of x values that will make this non-zero, right? So 1 and to positive infinity. So we can conclude that this is linearly independent. Oh, sorry. This is independent. Okay? So that's it. If you can find just one x value where it is not equal to 0 in the interval, uh, where the Wronskian is not equal to 0 along the interval, then that is automatically linearly independent. Okay? So the indication would be the Wronskian is not explicitly equal to 0. Okay? But you also have to be mindful of the interval, because not all intervals are -1, are negative infinity to positive infinity. Okay, so let's do the third one. Okay, let's do the third example. Y1 is equal to x plus 5. Y2 is equal to x, and then y3 is equal to 12. Okay, so let's set up the Wronskian for this. Okay, so x plus 5, we have x and 12. Okay, so the first derivative, so we will set up a 3 by 3 matrix here. First derivative is 1, and second derivative 0. First derivative is 1, then 0, 0, and then 0. Okay, so how do we determine the determinant of a 3 by 3 matrix? So for the first one, we do like this, right? So that will be x plus 5 multiplied by 1 times 0 minus 0 minus 0. So that would be 0. Okay? And then minus this one, second one. That would be x multiplied by 1 times 0. That would be 0 minus 0 minus 0. So that would be 0 also. Then plus. So the last one will be this, right? That would be 12 multiplied by 1 times 0. 0 minus 0. So that would be 0 as well. So this is equal to 0. So the Wronskian is equal to 0 no matter what x value in the interval negative infinity to positive infinity. It will always be 0 no matter what x value you choose within that interval. Okay, so therefore this is linearly dependent. Okay, so we've confirmed our results from the previous lesson, and yeah, so that's how you use the Wronskian. And many functions can be um, complicated and not as simple as this one. Yeah, but the process is the same. You just have to set up an n by n matrix and get the determinant, and then see if you can find a single x value where the Wronskian is not zero. And if that is the case, then you can conclude that it is linearly independent. Otherwise, if it is explicitly zero or all the values are zero for the Wronskian interval, then it is linearly dependent. Okay, so thank you for watching, and I hope you learned something from this video. Thank you. Thank you.